Welcome back, students. In this video, we are going to look at how to create alkynes. When we prepare or make alkynes, we use a similar reaction that we did to make alkenes. For alkenes, what we used was an E2 reaction. For this E2 reaction, what we needed was a leaving group and a beta proton, and our base came in, pulled off this beta proton. The electron swung around, made a pi bond, and it forced out our leaving group in order to form that alkene. Alkynes that have two pi bonds are created using two E2 reactions, right? So you just run the reaction twice. If you're running the reaction twice and you're not really doing it, it's just happening in the flask, then you need to make sure that you have a compound that has two leaving groups and two beta protons. So here I have 1, 2 leaving groups, and on my beta position, I actually have 3 beta protons, but I'm only going to draw in 2 because that's what's going to get pulled off during this reaction. My guess with your current knowledge is that you would go ahead and write this as your product. But there's something else going on here, and we're going to talk about it on the next slide. It has to deal with the fact that we've discussed acidity of terminal alkynes and the fact that you have excess of your strong base. Now, make sure that you know how your instructor or your textbook draws out the fact that you have extra of something. Some people will balance chemical equations. Some people will write excess in parentheses. Some people will write the letters X and S as the abbreviation for the word excess. Just make sure you're aware of how it's being communicated to you. Now let's look at what really is going to happen at the end. Because we have, again, 1, 2 leaving groups and 2 beta protons that are going to get pulled off, but there's still another proton here. So what you want at the end is this. But the problem is, in the flask, you have plenty of sodium amide. And we just learned in another video that that sodium amide, it's a strong base. You cannot stop sodium amide from coming in and pulling off this acidic proton. So this reaction that I'm about to draw, you cannot prevent that. It's going to happen. What you need to do is to make sure that you have plenty of sodium amide in the flask in order for that reaction to completely occur. And what you end up with at the end is an alkynide ion. Once you have that alkynide ion, you have two choices. You can either go through alkylation, like we saw in a prior video, or you can add water so that you can protonate that carbon that's negative. So let's add water so that we can go through the protonation step. We end up with our terminal alkyne at the end. Obviously, this is a special terminal alkyne because both sides have a hydrogen. So you could have the base remove a proton from either side or potentially even both sides of your terminal alkyne. But you remedy that when you end up adding water and you protonate whatever negative carbon is still present. Let's look at the overall reaction. For the overall reaction, you're going to be given something that has 2 leaving groups, and then you're also going to be given an excess of a strong base. A lot of times what happens is students forget that the first step creates the alkynide ion. And so then when they see the water, they're like, crap, what does the water do? And then draw really unusual things. So we need to stick in our brain that when we go through this process, if the alkyne is terminal, you cannot stop the alkynide ion from forming. And that's why you need water as a second step. So your overall product is going to be this. But after the first step, you make the alkynide ion. and then the water adds to make sure that you end up with a neutral compound at the end. When you see these reactions, it is common for you to see not only NH2 or NaNH2, you'll also see maybe NH3, or maybe even the NH3 below the arrow. It doesn't really matter. Then you look at this and think, what the heck is that NH3 for? Well, it's your solvent. NaNH2 is a solid, right? Sodium amide is a solid. It's an ionic compound. It makes sense that it's a solid. And it would like to dissolve in something, or at least we would like it to dissolve in something, because if our two reactants are in the same state when they're reacting, everything goes much more smoothly. What we do is we use ammonia, NH3, as our solvent because if our NaNH2 reacts and pulls off a proton here, guess what? There's no net change. You get the same thing as what you started with. Now here's the problem. When you're new to organic chemistry, you've spent so much time in general chemistry thinking water was the solvent for everything that sometimes we make mistakes and we add water. And if we added water to this in lab, we would not get what we wanted because the amide is such a strong base and water is actually kind of acidic in comparison. It's got a pK of 16. That what would happen is your amide would pull off this proton and you would get ammonia and hydroxide ion. The problem is hydroxide is not strong enough to make this reaction happen. So we need to make sure that when we're utilizing a strong base like sodium amide, that we're also choosing an appropriate solvent. Otherwise, all of our time and effort has gone and been wasted. Let's wrap up. In this video, we looked at how to prepare alkynes. We talked about how it was utilizing two successive E2 reactions in order to make those alkynes. And then if you had a terminal alkyne, another reaction would happen where you would form the alkynide ion. Sometimes you'll hear people say that this is the driving force of the reaction, which means that it makes the reaction happen. And your solvent is totally going to matter here because you have such a strong base that you cannot utilize a solvent that's going to interact with the base in any way and have that base be able to pull off an acidic proton. Thanks so much for watching. This is Katoni signing out.